And we're okay, we're recording. So all cells in any human, any non-human, any plant, any bacteria have electrically active membranes. Okay, in the chat right now, what I want everybody to do is just type any reason you believe that your body uses electrical activity in its nerves, muscles, whatever. If you don't know, just type I don't know. So everybody should type in the chat evidence that you have from personal experience that electrical activity is responsible for nerve function, muscle function in particular, and that your body depends upon voltage and current for the heart to beat, for muscles to work. So go ahead and type in chat and just type, if you don't know, just type I don't know. Okay, so, okay, what evidence do you have? Any evidence? When everybody type, everybody type. If you don't know, say I have no idea or I don't know. That's true. Electrical activity, that's true. What evidence do you have? Is your sound back? Okay. So IDK, that's good. If you don't know, you don't know. Any evidence that electrical currents are used in any body, any animal, any plant to accomplish sending messages through the body and muscle contraction and nerve function. Okay, that's true. Anybody else? Let's have an IDK. If you don't know, just type IDK. Thinking, okay, good. Electric eel, right, okay. Okay, anything else? Anybody ever have an EKG, electrocardiogram? Okay, good. Okay, so these messages will disappear. I may copy them all just to see who was here, okay? So let's get back to where we were here, action potential. So we've talked about the cell membrane with its hydrophilic heads and its hydrophobic tails. And we've talked about proteins that are inserted into the membrane. Many of these proteins provide a pore. These proteins are part of the process in establishing that the outside of the cell is negative compared to the inside. Okay? So, again, remember, these are the hydrophilic heads. This is the extracellular fluid. These are the hydrophilic heads. These are the hydrophobic tails. So like dissolves like. So all membranes have this bimolecular leaflet, a double layer of phospholipids. So there's different types of ion channels. And so, for instance, sometimes it may take an acetylcholine, a neurotransmitter, to open up a channel. And notice that there's more sodium on the outside of the cell and more potassium on the inside. So notice what happens. Sodium, calcium would flow in, and potassium there's more potassium on the inside, potassium would flow out. So it's called a ligand-gated channel, means that it opens because of a neurotransmitter. So here's our hydrophilic heads, here's our hydrophobic tails. Here's a closed channel that is opened by a neurotransmitter. We also have mechanically gated channels, meaning suppose somebody pushes on your skin and you feel it. Those channels could open on the basis of touch, pressure to the skin, and the movement of ions in and out of the cell leads to changes in voltage and movement of usually sodium in and potassium out. So potassium tends to flow out because there's more potassium on the inside. Sodium tends to flow in because there's more sodium on the outside. So these are charged particles, sodium plus and potassium plus. Other type of channels are open when the voltage changes. So the voltage is minus 70 millivolts. Compare the inside of the cell to the outside. So if potassium is leaving, that's going to make the, that's wrong. Okay, so anyway, some channels open in respect to changes in voltage. And how does voltage change? By the flow of potassium out, for instance. Okay, so those are voltage gated channels. There's other channels that leak. They leak potassium and they leak sodium in. Okay, so because there are charged particles inside the cell and there are charged particles outside the cell, when you have a reference electrode and you stick a very, very, very small piece of glass that's been pulled to a point and is open at the end, you measure that the inside is negative to the outside of the cell. There's a lot of proteins and other molecules that stay inside the cell. So even though there's potassium that can move out and there's sodium that can move in, overall the inside has what's called a resting membrane potential of minus 70 millivolts. So if you take a voltmeter and have a reference electrode and this very, very fine recording microelectrode, you can measure that the inside has excess negative charge. So remember, we have our hydrophilic heads, hydrophobic tails. The inside has an excess of negatively charged large molecules and potassium. The outside has an excess of sodium and calcium. Okay, so let's stop there a moment, or let's say any questions. Oh, someone wants to join. Joanna Harris, okay. Okay, so is everybody still hear me? Somebody say yes, type yes to something.
Yes.
Everybody still hear me? Okay. Okay, so let's stop recording for a moment.